Thanks, Emma, for the introduction, and I'm honored to be speaking here. Thanks everyone for your patience and coming back half an hour after the originally scheduled time. So my talk is about proxy objectives, and speaking of misplaced priorities, this morning I was just sitting in Starbucks and having my morning coffee when I got a call saying that I was supposed to be speaking right now. And it turns out there's a little time zone mishap, and I thought my talk was at noon, so thought I would have a leisurely morning to finish up my slides. But so that's why I'm standing here with a swimsuit and funny-looking socks. I didn't want to delay the talk anymore by going off to my hotel room to change. Okay, so my talk will be about proxy objectives in reinforcement learning from human feedback. So first, let me define the terms I'll be using. So a proxy objective is just an approximation or an estimate of the true objective that you really care about optimizing. And I'm going to use the term over-optimization, which means that when you optimize the proxy objective too far, the true objective starts getting worse after maybe an initial period where it gets better. And I used over-optimization instead of overfitting because overfitting is usually associated with estimation error or noise, like you have a finite training set. Whereas there's a more general phenomenon that you might even have in a setting without any estimation or sampling. So proxy objectives are all over the place in machine learning. One extremely basic example is that the gradient is an affine approximation to a differentiable function that you're optimizing. And then there are some other key methods in optimization where you repeatedly construct a local approximation to your objective and then solve that subproblem. So some examples are sequential linear programming and also quadratic and convex programming. And some of my earlier work involved studying reinforcement learning in this lens and trying to figure out, if our true objective is to maximize expected reward, what kind of local objective can we construct using some recently sampled trajectory data and using that and building optimization algorithms around that. So building on some earlier work from Kakad and Langford, we proposed a surrogate objective, and surrogate is basically a synonym for proxy, which looks kind of like an importance sampling estimator of the performance of a new policy, pi tilde, where you're just ignoring the effect that changing the policy has on the state distribution. So you're accounting for the change in the action distribution given your current state distribution, but you're ignoring the effect on the state distribution. So you can write down this objective and it's easy to optimize. And policy gradient methods are essentially doing something like this. To build an algorithm that learns reliably, you can do something that's very common in all of these optimization algorithms that use proxy objectives or a series of subproblems where you create a trust region, which means like some region where you think your local approximation is valid, and you solve the optimization problem like while constrained to the trust region, or you use some sort of something like a soft constraint instead of a hard constraint. So that's a penalty, which says don't go too far from your starting point, which is where the local approximation is valid. Okay, so there's also lots of instances of over-optimization in the real world and in society. So Goodhart's law is, the term was originally coined in economics by Goodhart, and this wasn't the original statement of the principle, but it's something like when you have some measure or metric and you use it as your target, it ceases to become ceases to be a good measure. So that means something like it ceases to track the actual thing you care about, even if maybe it originally tracked your true objective. So people talk about this a lot in the context of in economics or in in public policy. So a common pattern is that you have some government or institution that creates an incentive, and that seems reasonable given the current state of things, but then it gets optimized in some perverse way that the creators of the incentive didn't anticipate. So one very classic example is this Cobra effect, where the British colonial government in India wanted to reduce the population of cobras, so they created some kind of reward for turning in dead cobras, and then people started breeding cobras to turn them in. So this is like a classic example in business school courses and so on. And there's also lots of instances where there is some metric that was intended to stimulate production, like in a planned economy, and it turned out incentivizing the wrong thing. So on the right-hand side there, you see this is a Soviet-era cartoon of some factory which has just produced a giant nail, presumably because there is some kind of quota around the total amount of weight you produced in nails, and this is a way of optimizing that metric. So my optimization-based interpretation of all these phenomena is that the incentive was actually correct for local changes around the current state of the world when it was imposed, when this incentive was imposed. So this was intended to induce some change in the behavior distribution, meaning the behavior of the populace. For some very small perturbations of behavior, this incentive was correct. It had the correct gradient, but people optimized much further than intended. And so the incentive actually started pushing in the wrong direction at a certain point. And maybe if you had some kind of regularization that said, behave normally, don't do anything weird like breed cobras, you would avoid these problems, but that's pretty hard to do in practice with actual humans involved. So this is a little bit of a wishy-washy slide, but so I don't think there's a general theory of over-optimization because there are lots of related phenomena, but there are a couple of general recurring patterns. So so vaguely speaking, one idea is that if the true objective is sort of a quadratic, meaning it has an optimum somewhere, and it's kind of smooth around the optimum. And then when you optimize the proxy objective, you go really far away from your starting point, meaning you follow some curve that goes really far, or some line that goes off to infinity. Then you're going to, of course, see some over-optimization behavior where the true objective goes up and then down. So I think this explains a lot of what's going on. Another case that comes up a lot when you have proxy objectives that are estimated is that you have different parts of your input space, and some parts of the input space you have a lot of data, and other parts you don't have any data, especially if you have a high-dimensional input space. And what's going to happen is the proxy is going to be poorly estimated in some parts. You'll have huge error bars there, and then probably it'll be highest at those points where the error bar is large. So here on the bottom right, I tried to show the estimated rewards for a bunch of actions in a bandit problem with error bars. So you can see that there are a couple of actions on the left that have medium to high rewards and small error bars, and then there's a few on the right that have big error bars. So you might expect that so the ones with the high error bars might have just gotten lucky a few times and gotten a higher than average reward or return. So if you try to just select an action or a policy based on your past data, you run into this problem a lot. You find some kind of out of distribution action that you don't have much data for. And this is a big problem in something like offline RL, where you have a bunch of a fixed data set and you're trying to figure out the best action or the best policy from it. So you need to do something like have a penalty that keeps you from going too far away from the behavior policy, or maybe you do some kind of lower confidence bound thing where you take mean minus standard deviation and use that to select your your action or your policy. Okay, so now let's move on to reinforcement learning from human feedback. So this is, on this slide, I'll just briefly describe the whole thing, like what the algorithm is. So for those of you who are familiar with RL, what we're basically doing is we have a contextual bandit problem, and we're doing model-based RL on it, or offline RL on it, where we fit a model to the reward function, and then we optimize our policy against that. And it's a contextual bandit problem where the observation is the prompt. So it might have an instruction, or it might be the previous few messages of a chat. And the action is the completion, so what the model writes next in response. So for example, in the summarization case, you might have text to summarize, and then the completion would be the summary. Or in a chat, the prompt would be all of the previous messages, including the last user message, and the completion would be the last assistant message. So here's a minimal description of the algorithm. We have some initial policy. Sometimes we use supervised learning to get this initial policy, where we just collect human demonstrations and fit the policy using supervised learning. And let's say we also have some prompt distribution. We sample a bunch of completions from the current policy. Then we have to query a human on each prompt completion pair and ask them what reward that prompt and completion should get. And then we fit a reward model, meaning we fit a model to these reward queries that we collected from the human. And then we optimize the policy. We optimize this. We optimize expected reward with respect to the policy. And that means we're going to be sampling lots and lots of completions on our prompt distribution, and observing the models, the reward model, and doing RL updates. So what we actually do in practice is we use PPO to do this policy optimization step, using this model to define the reward function, this reward model R. And usually we add a little bit of a KL regularization that says, don't move the policy too far away from the initial policy, which we use to collect all of this reward modeling data. Because the reward model is only accurate for samples that, like around the original policy, or for things that have reasonably high likelihood under the initial policy pi 0. So if we optimize the policy too far, the reward model wouldn't be trustworthy, and it would probably be very wrong. So this gives us one policy update. We optimize the reward model for a while, and then we stop at a certain point, and now we have a new policy, which is hopefully better than the old one. We might have to do human evals of many checkpoints along the way to see which one is the best, because we're only measuring the reward model during training, but we actually care about the human preference. So we might have to do human evals as our ground truth to do early stopping. And so then we get this new policy pi 1, and now what we can do is go and collect new reward model data from this policy. So we go and query humans again from using samples from pi 1. So now we have a reward model that's also valid around pi 1 samples, and then we can optimize pi 1 further to get an even better policy, and so on. So it's actually, this algorithm has a few different layers of loops. Like so PPO is actually on the inner loop. Like doing many iterations of PPO is on the inner loop, where each of these iterations you have a fixed data set from humans, and then in the outer loop we're collecting new human data to make sure the reward model is valid. So one question you might have is why use this model-based RL algorithm at all? Like, why not just query humans while we're doing RL and then just update the policy directly? Like, why can't we just skip the reward modeling step and just update the policy on the reward queries from humans? And the reason is just for sample efficiency, and also for like while you're doing development, sometimes you have to do multiple RL training runs with different hyperparameters. So it'd be pretty terrible if you had to go and recollect all your human data whenever you want to do a new run because you had the learning rate set wrong. So it's not just about sample efficiency of a single run. It's also about being able to do hyperparameter tuning separately from your data collection loop. And I think one interesting open question is just how big is the sample efficiency boost that you get from doing model-based RL this way? I would guess that there's a decently big boost, but I haven't seen this measured really carefully. Here's just an illustration of the same idea, specifically for the summarization case, which will also illustrate one detail I left out, which is that we collect pairwise feedback, where we actually take two completions at a time, and we have, or more than two completions, and we have a human rank them, as opposed to just asking a human for an absolute rating. How good is this completion? And that's just because it's easier, because it would be hard to write such a detailed rubric that people would have consistent absolute scores. So it's easier to do a comparison. But this doesn't actually change the algorithm that much. It just means when you fit the reward model, it's fit on this loss that involves pairs of completions, which tries to minimize some ranking error, or it's basically a classification loss involving pairs of completions. So you fit this reward model, and then you just use the logit from the classifier as your reward function for RL. Okay, so this figure on the left is from the original, from the summarization paper, Learning to Summarize from Human Feedback back in 2020. So this is a classic over-optimization plot doing one step of, or running PPO on a learned reward model. So you can see that the predicted reward, according to the reward model, is just going up monotonically. Whereas when you actually query humans about their preferences, it goes up for a while and then it starts going down. Yeah, so this, and the way, so on the x-axis, we're actually looking at the KL divergence between the initial policy, which was trained using supervised learning, and the updated policy, which is obtained using RL. And you can do an easy Monte Carlo estimate of this using samples from your updated policy. And on the right, you can see what some of the over-optimized samples look like. Might be a little too small to see, but basically there are certain phrases that get used repeatedly, like the word thought-wise and please help. So it seems like the reward model really likes a couple of these phrases, maybe because there's one or two winners in the comparisons that had these phrases, and it just the RM has some quirk, and then optimization will just put this everywhere because the reward model likes it. And of course, if you did another iteration, you'd fix this problem because humans would label these over-optimized looking samples as being terrible, and so you would get rid of these quirks, but then the next iteration you might have different ones. So you're playing a bit of a game of whack-a-mole. By the way, since we're using pairwise comparisons, we don't have this. We don't have a scalar absolute reward to look at. So the y-axis here is. The y-axis is just a win rate. So you just compare a sample from the supervised policy and a sample from the new policy. And you can also do things like calculate ELO scores if you have a family of different policies, and you don't want to compare every policy to every other policy. So we've seen some similar kinds of issues in ChatGPT, and in fact, some of the annoying behaviors that people have pointed out are the result of over-optimization, we believe. So for example, one thing you commonly get is excessive verbosity, where you have very long answers, and some of them have lists of lists of lists. And yeah, some of the other issues like the model apologizing, like sometimes it'll apologize at the beginning and the end of its response, which is a little annoying. Or there's certain phrases it likes, like as an AI language model, or it'll say something like, it'll talk about its knowledge cutoff, because maybe originally we had some problems where it was hallucinating. So then we trained it to, then we collected some comparison data that preferred completions that instead decline to answer and say something about a knowledge cutoff. And then the next iteration, we would get lots of refusals like this, where the model talks about its knowledge cutoff. Oh yeah, hedging is another thing this actually relates a lot to calibration and truthfulness. So this is a very tricky issue, like how you get the optimal amount of hedging, but you can easily over-optimize and get way too much of it. And also just having the model refuse queries that it shouldn't. So I'm going to talk a little bit about some of these studies my colleagues and I have done to study over-optimization quantitatively. So, and to do this, it's hard to do this with human data as the only ground truth reward that you're looking at, because it's very expensive to collect human data and it's noisy. So if you want to draw some learning curves and do sweeps over model sizes, you can't really do that with human data. So for the work I'll be talking about, most of the work I'll be talking about, we use the following simulated setup for RL from human feedback. So we trained a large reward model on our full data set of comparisons. So this maybe had 100,000 examples, and actually this wasn't that big of a model. This was a couple years ago. So this is one of the smaller models from the GPT-3 series. So I think it had 6 billion parameters. So we trained our large reward model on, we trained this large reward model on the full data set, and we call this the gold reward model. And then we can query it at new prompts and completions to create new synthetic comparisons. And then we can train smaller reward models on these synthetic comparisons. And so we treat the gold reward model as effectively the human. And we can see what happens if we go and optimize on our these smaller reward models trained on synthetic data. What happens to the policy? Does it get worse on the gold reward model? There's also a recent paper that proposes, it's called Alpaca Farm, that actually has a more realistic setup for doing simulated RLHF that came out more recently. So they use a set of simulated annotators that are each defined by different prompts, and there's some label noise, which they found to be important. So that I think that's a good simulated setup for more future work. But okay, so here I'll show some plots that show the over-optimization behavior. So first, let me. I'm going to talk a little bit about this best of n algorithm, which is very simple, but let me just describe it quickly. So in the best of n algorithm, you have a policy, which means a policy that in this contextual bandit setting, it just samples completions given prompts. So it's a language model. So you have your policy and you have a reward model, and you just take n completions from the policy for a given prompt, and then you score them all with the reward model and take the best one. So so that's the best of n algorithm. And so we can draw this frontier of reward versus KL for both the best of n algorithm and for doing PPO. So here we're doing best of n and PPO on the small reward model that was trained on synthetic data, and then we're evaluating it using the gold reward model. So you can see that in both cases, for both our for RL and best of n, the reward, the true reward, which is the solid line, goes up, and then it goes down a little bit, especially for RL. Whereas the dotted lines, which are just the synthetic, which are just the proxy reward, those just keep going up. So we're, by the way, we're using KL to measure how much optimization power we put into our proxy objective, how hard we optimize on the proxies. So for RL, this is easy to estimate with just a Monte Carlo estimate. For best of n, it turns out you can compute the KL between the best of n policy and the original policy analytically. And this is a very cool and non-obvious fact, which I'll explain in a couple slides. And it turns out it goes with log of the number of samples. And if you look at the plots, you'll see that they actually, maybe if you squint a little bit, it looks kind of like the RL plot is the best of n plot, but with the x-axis stretched out. So that kind of means that you can think of both algorithms as spending KL. Like in both cases, you're moving probability mass from some of the low reward samples to the high reward samples, and this is incurring KL. And this plot shows that RL is spending KL less efficiently. So it's moving some probability mass around uselessly, but whereas best of n is just moving it all around, just the way it needs to be moved. So here's a plot that shows some scaling behavior. So it's, I mean, the reason we wanted to study the scaling behavior is so we could understand what happens if we scale up our models. To what extent do we see more or less over-optimization? And like, are there algorithmic interventions that'll lead to less over-optimization? So to figure these things out, we wanted to really understand, better how over-optimization works in this setting and how it scales with various things. So one kind of clean scaling result that we got was that we could scale the size of the proxy reward model, and this would produce a predictable effect on the over-optimization behavior. So here in the solid lines, you can see what happened to the gold reward as we optimized the proxy reward. And very faintly in the dashed lines, you can see the proxy rewards, which just go up. And the big models are the yellowish colors, and the small models are the purplish colors. So you can see that for the small proxy reward model, you get over-optimization pretty quickly when you're doing best of n. So you can see after best of 4 or so, the results start getting worse. So, and that, so that's not very hard, like that's not selecting very hard on this objective. So it's kind of, so this is a very bad reward model if just using it to select best out of 4 is the most selection you can do before you start getting over-optimization. Whereas then for the bigger reward model, the bigger proxy reward, like with 3 billion parameters, which is yellow, the true reward just keeps going up monotonically as we increase the number of samples in best of n. Actually, I said the wrong thing. I said it was best of 4, but that's wrong. It's the x-axis is KL between the best of n policy and the original one. So KL of 4 corresponds to like best of 30 or something. Whereas a KL of 10 is something very large, like 10,000. Okay, so for RL, you get a kind of similar looking plot, maybe a little bit noisier, but because there's just more in the experimental setup going on. But you can see for the small models, we get over-optimization very quickly at fairly low KL. The whole KL axis is stretched out a lot because RL incurs much higher KLs than best of n. So you can see that for the small models, which are blue, the over-optimization happens pretty quickly, whereas for the large ones, which are yellow, we don't even see any over-optimization. The true objective just monotonically improves. So we tried to see what kind of functional forms would fit these curves best. And we found that best of n and RL had slightly different functional forms. So a quadratic function fit best of n pretty well, whereas we had this logarithmic, this difference between linear and x log x for RL. And actually, it turns out if you just, the RL one with x log x is, if you use some power like d to the 1.1, you also get a reasonable fit. So the key thing is just, it's not a power of 2 there, it's some power very close to 1 there. And actually, by the way, when I saw this result, I thought it was a kind of weird function, and I doubted it a little bit. So when my co-authors had come up with this, so I had them send me the data, and I did the fitting, and I was actually surprised that it just this x log x function actually fit much better than anything else. Like I thought maybe anything that goes up and then down will fit decently well, but it turns out that this actually fits really well. So I think there's something real going on here. By the way, here the x-axis, we use the square root of KL. That's because KL kind of behaves like a distance squared. Like if you interpolate along a line from the initial policy, the KL will, if you linearly interpolate, the KL will go up quadratically. So using the square root of KL often produces nicer looking, linear looking plots. Okay, so here, this is just a neat bit of math, which is that you can analytically compute the KL between the best of n policy and the original policy. So the explanation is, let's say, okay, so you can, the core idea will be that when you do best of n, you're moving around probability mass from the high reward samples to the low reward samples. And all that really matters is the ranking of that sample. And that determines how much probability you're going to move to or from that sample. It does, nothing else about the distribution matters. So yeah, so the basic idea is if we have some random variable x, which is like our completion, and the reward has some distribution. So we can calculate, we can take the CDF and look at the percentile of a given sample under that distribution. So this like CDF has a uniform distribution. So in the plot, you can see the purple curve. This is like your initial uniform distribution. So then when we do best of n, so you can calculate that, you can like do a pretty simple probability argument that shows that when you do best of n, like the density, like samples that have a higher value of f of x will be more likely to be the one chosen in best of n. And the probability density ends up being n minus 1 times u to the n minus 1, where u is between 0 and 1 is the CDF value. And then you can just take the KL between that density and the uniform distribution, and then you get that it's this expression log of n minus 1 over n. So I think that's pretty cool. And you can see in the plot how the density changes when you do best of 2, best of 4, best of 8. So you can see that the probability density becomes 0 for the worst samples, the worst ranked samples at the left side, and then it becomes higher on the right side. Okay, so from so far I've been talking about over-optimization, and this is a big problem when we're doing RLHF, and it prevents us from getting really good results. But this isn't actually the only issue, and if we're going to talk about proxy objectives, we might as well look at all of the places where we have proxy objective that's where the thing we're optimizing is not exactly the thing we want. And so to do this more thorough analysis of where we have mismatches, we can try to do a whole error analysis of the whole system. And okay, so like roughly speaking, we have several different sources of error. So the reward model just might not be able to approximate the preferences very well. For one thing, it doesn't have the reward function is just a classifier that just has one token to do its calculation. So it doesn't get to do chain of thought, and it doesn't get to do like some kind of like deep computation. So, but it also doesn't have access to ground truth knowledge, and it can't execute code. So like in the normal version of RLHF. So yeah, the RM just might not be able to approximate the preferences very well. So this is a kind of approximation error. The reward model is often going to be overfitted to the training comparison. So we have some estimation error on the reward function. So that's just the reward model, but then we have another bunch of sources of error on the policy side. So the policy like often hasn't fully optimized the reward model on the training prompts, even while we're doing the RL step. Like you saw in some of the previous plots, that true objective was still going up monotonically at the end of RL, so that can still happen. Of course, the policy could also be overfitted to our like finite and undiverse set of training prompts. And also the policy model might just not be able to approximate the optimal policy, like it might just not be able to do the computation we want it to do. I like the breakdown in general into optimization error, estimation error, and approximation error. It doesn't always completely make sense when you're in an overfitting or over-parameterized regime, but I think it's useful anyway, especially for RL, where you do often have optimization errors rather than overfitting. So that's okay. So that's a bunch of different sources of error that we might have, but actually, there's another giant one, which I think will be the main one, like increasingly important in the future, which is that actually, when you go and collect a data set by hiring people to collect labels, this also isn't a very accurate approximation of the thing you actually care about. Or also if you try to collect labels from users or try to use some implicit feedback from users, like how engaged they are, that has different problems. So yeah, any kind of comparisons that you collect realistically is going to be a proxy for what you actually care about, and there's a huge additional source of error here. Okay, so what are all these issues with the labels? So there's generally going to be a mismatch between the preferences of whoever you hired to do the labeling and what the users of the system actually need. So one obvious case of this is most people who have done RL from human feedback have encountered some issue with completion lengths, like with getting excessively long completions. And I think this is generally because users are waiting for the completions to stream in, so it's annoying if the completion is too long, whereas the people doing labeling often either have a pre-computed completion or they're doing a lot of thorough analysis, so they don't actually care if it takes longer to stream. So I think there are just biases created by the setup there. Also, I think when you just hire people to do labeling, they're in a different state of mind than the users. Like they're just they're doing their job, so they're less in the mood for fun and friendly behavior. They're gonna like try to just look for. They're gonna try to follow the rubrics, but they're not gonna necessarily look for a lot of flair, and so you might end up with a boring, boring behavior. There's a different set of issues when you try to use labels from end users or from, or if you try to use metrics like engagement that you measure indirectly. So, I mean, there are all sorts of problems with trying to optimize for engagement and so forth that are well known from recommender systems. So one thing is that for recommender systems in general, you might have some kind of want-should conflict, like I want, I want to eat the donut, but I should eat the healthy meal. So people might want something like that's mindless entertainment, but they should have something that's correct and informative. And also, if you're not careful, you'll have a model, and you train a model on user preferences, you'll have a model that has that's kind of sycophantic, and it just agrees with the user and tries to figure out what their views are and shows them exactly what it thinks they want to see, and that's going to be a big problem. Yeah, there's also these are just issues about having a slightly wrong objective, but there's also issues around just being able to label, being able to do tasks that are very difficult or involve challenging technical material. So imagine you ask a model like ChatGPT a hard coding question, and you get you get a couple of very long responses. Well, you might be able to go and test these out yourself and see which one works better. Though not always. I mean, you might be asking about something that you can't easily test. But imagine if imagine if you're trying to label some data that involves some libraries that you're not familiar with, or some topic that's very challenging. It's going to be very hard. So I think just getting high quality labels in hard domains is very hard. And if you're not careful, you'll get we'll train the models to output things that look right in hard domains, and that are right in easy domains, and just look right in hard domains. So I think the big area for improvement here is figuring out how to assist human labelers by using the models. So I think human plus AI is going to be better than AI alone for the foreseeable future, and we need to figure out how to make human plus AI as effective as possible. So, well, we know a couple days ago there was a big groundbreaking announcement about room temperature superconductivity. So it would be cool if our models could help us figure out, analyze something like that. But this is a pretty technical, and if the model were going to give me a good answer to this question, it might have to catch me up on lots of background material on condensed matter physics. So I might have to read. There might be pages and pages of content needed to justify its answer. So in general, it's easier to verify than to generate completions. And this is why RLHF, this is one of the main reasons why RLHF works well in the first place, because it's hard for people to write long, high quality things, and it's easier to just compare them and check them. But often it's still very hard to verify things, because you might need a super long justification, or it might require a lot of background material. So there's a hypothesis that there's some benefit to using an adversarial or multi-agent setup where you have one agent. Well, you have one copy of the model that produces the original answer, and then you have another copy that critiques it. And the idea there is, even if the original answer or the justification for the answer is extremely long, the critique might be able to just point out the weakest point in the argument. So for this, obviously would work for something like a proof where you can check it locally. Each step can be checked, and if every step is correct, the whole thing is correct. And it's a little less obvious for something in an informal domain, but to some, it's probably has some truth to it. And in fact, there's a nice experimental validation that critiques are useful. So this is in this heat map, the y-axis is which policy was used to write the critique, and the x-axis is which policy was used to do the task. And you can see that as you go towards bigger models, the model can critique itself better. And the goodness of the critique is just judged by a human. Like, was this critique helpful? And the task here was, this was a topical summarization task. So there was a long passage and then some question that asks the model to summarize with a certain aspect of the passage in mind. So there's another. So I think this is actually a really interesting problem conceptually of how can we how can we create an algorithm that'll produce higher quality labels or rankings than an unaided human could? So just to sort of motivate the problem and why it's hard, imagine your task is to come up with an optimal chess move given a fixed chessboard. And you're not a chess expert, let's say. Um, so you want to figure out the optimal move, but you're in the room with one or two chess prodigies, and you think they know the right move, and you can reward them with a cupcake to incentivize them to tell you. So the question is, what do you do? I mean, if you just say, tell me the right move, and then I'll give you the cupcake, then how do you know they're actually giving you the right answer? They could have just told you any old move. Um, so, so imagine there's just one chess prodigy in the room. Actually, it's not clear that you can do. It's actually not clear that you can do anything there, because maybe you can say, "Play me in chess, and if you win, I'll give you the cupcake." But if the prodigy knows that he's way better than you, he doesn't need to take a good first move. But then if you have two of them, then actually there is something you can do. You can just say, play against each other, and the winner will get the cupcake. And then you just observe what the first move was. And since they're both trying to win and they're playing this zero-sum game, you can be pretty sure that they're at least incentivized to take the optimal first move. So I think this is a really valuable insight, and I think the general setup here is something like there's a sort of mechanism design problem. You have a weak agent, and then you have one or more stronger agents, which presumably have access to more knowledge or more time to think, or can do more computation, and the weak agent H, which is like the stand-in for the human, is given a task that it can't solve. For example, assess this paper on room temperature superconductivity. And the question is, can H define a reward for the strong agents so that the optimal or the equilibrium behavior is to actually give a helpful solution? And something where so there's a nice line of work on debate that basically uses this idea, and this idea provably works for certain like very formal problems like solving certain logical certain like solving certain kinds of logical problems or calculating the move in a game like. This will clearly work. It's a little less obvious how much it works in something more realistic, like a question answering setting. So that's an area for future work. So just to summarize, I talked a bit about proxy objectives and Goodhart's law in general, and these phenomena are pretty ubiquitous in both optimization and in life. And in RL from human feedback, we're using a model-based algorithm, so we end up encountering this phenomenon and it's very crucial to solve it or to overcome it. And we can simulate this over-optimization phenomenon to study it better, and we see some reasonable scaling behavior. And lastly, there's the last kind of proxy objective that's important is that the human labels are also a proxy for the thing we actually care about. And so the next frontier is figuring out how to get higher quality human labels by creating some better task design or doing some mechanism design that further reduces the gap between what we're optimizing and the thing we actually care about. That's all. Thanks for your attention.
Hi, thank you so much for this great presentation. So it seems like for a lot of the ground truth labels, you rely on humans, right? So my question is, if we want to someday build a superhuman AI, then how are we going to get past this?
Yeah, I guess there are two answers. So you could have some kind of you could have some kind of ground truth labels that you get, say, from some source that the model doesn't have access to. For example, predicting the future, or you can also try to you can do something like what I was describing at the end of the presentation, where you try to amplify the human feedback or somehow assist the human labeler and exploit the fact that it's easier to verify things than to generate them.
Thank you very much.
Hi, John. Here.
Oh, hey.
Hey, thank you so much for the fantastic keynote. So I have a question about the methods which came out in the last half a year, in which people try to do something similar to RLHF, but not using RL methods explicitly, instead replacing them with supervised losses or ranking losses, so papers like DCO or REFT. I wonder if you have any thoughts on the comparison of true RLHF versus those like non-RL methods, and whether there is any difference in terms of reward optimization, over-optimization.
Oh yeah, I think this is still an open question, how some of these other methods compare to the RLHF pipeline I described. I'd say that some of these methods aren't actually that fundamentally different. So for example, you have, for example, direct preference optimization optimizes, uses a ranking loss directly instead of like first fitting a reward model and then using this logit as a reward. But you could also do a version, I guess you could do something that looks like the, that kind of looks like PBO, and that it samples lots of completions and then use this other objective. So I think there's like a couple of different axes that you can vary independently, like what objective you use, whether it's using the rankings in some native way or whether it's trying to like fit a reward model and then using the logit. And then there's whether you have an offline algorithm or an offline algorithm, meaning something that never samples during training, or if you have something that's more like an online algorithm that samples during training.
Thank you.
Thanks for a fascinating presentation delivered so calmly after being advised of your time zone incident. You mentioned Goodhart's law in the context of over-optimization and how policies that seem initially reasonable can lead to unintended consequences. So what unintended consequences can you imagine as a result of casting many activities as optimization problems for machine learning to solve?
Yeah, that's an interesting question. Well, I'm sure they're going to, I can't think, I don't have any good examples off the top of my head, but I could definitely imagine that just the act of turning something into a problem that you can address with machine learning would require some kind of reduction of the problem that would miss the important elements of it. Yeah.
Thank you.
Hi, John. Good morning. And thank you for your excellent presentation. And coming in the morning with a lovely casual race, you have conquered I think, the hall. The same way in last November, we are all waiting anxiously for GPT-4. And in it all casual form, ChatGPT came and conquered the heart of the millions. Now coming to your actually human feedback based RL, I have a question actually, which you try to answer, but at present, what is going on? Because, you know, if you take feedback, sometimes it introduces optimization, the over-optimization, because policy gradient becomes locally biased. And are you trying to model some kind of human behavior? Because the way we are prompting and spread it across the world, and if you take them randomly into the policies without proper behavior modeling, then all kind of problems may occur. So what is the future of human feedback based RL?
Yeah, well, I guess there are a few questions there. I mean, I think there's still a lot to do in making our current systems better, like reducing hallucinations and making them more fun to interact with, and making them better at certain tasks that are useful to people. So yeah, there's a lot to do there. I think some of it will require just getting the basics right, just taking the stuff that I already presented on and doing it better. And then some of it will require new techniques to do things like assist the human labelers. So I'd say these are some of the things we're working on now.
Okay, thank you.
Yeah, thanks for the great talk. I wanted to ask you about sort of the RLHF pipeline, in that something that's a little bit interesting about it to me is that we typically fit our reward model on one set of prompts that we have our responses for, and then we actually do PPO on another set of unlabeled prompts. And so in a sense, we're sort of doing this like self-supervised or semi-supervised learning. You mentioned direct preference optimization earlier. In this setting, we don't have two separate sets of prompts. We just, fit our policy on our data set where we have our paired responses. And I wonder, to what extent is it useful to do this learning on unlabeled prompts? Are we getting anything extra from them beyond just, however well our reward model generalizes? Because it seems like that's sort of our limiting factor there. So yeah, I wonder how you think about this, like learning from your own samples on unlabeled prompts and whether that's important.
Yeah, I think that's still an open question. So it's not clear whether the unlabeled prompts help. It's kind of, you have, to what extent can you just have an offline algorithm that doesn't do any sampling during the training step? My guess is that the unlabeled prompts actually do help because there's always going to, because of this gap between like how easy it is to generate something and how easy it is to check it. So I think the ability to rank, or the reward model's ability to judge things, is always going to be a little bit ahead of the policy's ability. So even if you, well, I don't have a really compelling answer, but my guess would be that there's, if you have a limited number of prompts with actual comparisons, you can still squeeze something out of the other prompts, which will improve generalization. But this is an open question.
Thanks a lot.
Thank you, John, for your wonderful talk in this early morning. I just want to ask, why did your team choose ILHF as the algorithm to inject human knowledge into the model instead of something like supervised learning or imitation learning?
Well, we tried a bunch of things, and this worked the best. So, yeah.
Thank you.
Hi. Yeah. Thank you for the talk. Am I understanding correctly that the current goal of our LHF is aligning models with the universal values that many human annotators or labelers can agree upon? And what do you think about some statements and claims like we need to think about aligning models with regional like standards or even personalized value of a specific user?
Yeah, I would say that right now we are kind of optimizing for some aggregate preference from all the labelers or whoever we're getting comparisons from, and this is a decent choice, but it's maybe not exactly what we want. Different people are going to have different preferences. To some extent, you have like when the model has a context, it is. Well, depending on exactly how you collect the data, you might end up getting some personalized behavior. But I would say it's not totally clear to what extent you even want to personalize a model. You definitely want to personalize it somewhat, but for example, I don't think we should give people wrong answers based on whether we think that person would prefer the wrong answer. So yeah, I think it's actually pretty subtle, and yeah, I think this problem will require a lot more careful thought later as we get really good at optimizing preferences. Right now, I'd say there's still a ways to go in just trying to optimize whatever aggregate preference function we have. And we don't have to think too hard about the fact that we're not exactly like optimizing exactly the right like distribution of human preferences. But I think that'll be a bigger issue later. One idea I like is if you can, that maybe we can extract some kind of legible representation of individual preferences or different groups preferences, so legible meaning it's like written in text, and then we can decide which parts make sense to keep, which parts the model should use, and which parts it shouldn't. Yeah, there's also there's some work from OpenAI on democratic input for these systems and collecting, trying to use systems like there's this thing called Paul.is, which is used in Taiwan to do policy, like get public input on policy. So there's like a project on trying to use this kind of system to get different people's opinions and possibly use that to determine what preferences the model should optimize.
And on that, due to time, we're going to halt the discussion, but please come up to John afterwards to ask questions, and we'll have the poster session now. Thanks again.